Compare two numbers. Tens come first, then compare ones.
The golden oak grove is preparing for winter, and up ahead, Juniper the red squirrel is working entirely on instinct, gathering her autumn harvest from the forest floor. As she works, Juniper follows a highly specific method. She gathers her acorns into tidy, consolidated caches of exactly 10, leaving any leftovers as scattered individual pieces. If another squirrel builds a pile nearby, deciding who has more becomes a challenge. Counting every single acorn one by one would take all afternoon. But there is a faster, mathematical way to find the answer. The wise Math Sheba watches the forest floor and teaches a reliable system to sort it all out. The rule relies on a strict hierarchy. You evaluate the large caches of 10 first. The loose ones only matter if those 10s are perfectly tied. Down on the moss, we can observe two distinct, fully sorted harvests resting side by side. Left is 3 10-acorn caches and 4 loose ones, 34. Right is 2 caches and 8 loose ones, 28. Compare the full caches. 3 10s is larger than 2 10s. The scattered ones cannot close the gap, so we record 34 is greater than 28. A single consolidated group of 10 naturally overpowers any collection of scattered individual units. The tens digit dictates the outcome right from the start. But as the harvest continues, a new scenario emerges. From a distance, 2 fresh piles look almost identical. This visual arrangement highlights the complication. The harvest of 45 and 42 each contain exactly 4 full caches of 10. The primary rule leaves us in a deadlock. When the primary value ties, we stop looking at the 10s and immediately shift focus to the loose units. Matching the loose ones directly, we pit the 5 individual acorns on the left against the 2 on the right. 5 easily beats 2. This decisively resolves the tie. We place our symbol to record that 45 is greater than 42. The ones place exists strictly as a structural tiebreaker. By evaluating numbers progressively from left to right, the place value system guarantees a clear answer. Let's examine one more layout. Down the log, a smaller harvest of 57 sits directly adjacent to a larger pile of 63. Applying our first rule, we evaluate the 10s. 5 caches is distinctly less than 6 caches. We mark the relationship with a forked twig symbol. The open side always faces the larger quantity, opening wide toward 63. Because we read equations from left to right, the pointed tip comes first. We read this as 57 is less than 63. No matter which side holds the larger amount, the physical orientation of the symbol dynamically adjusts to map out the exact size relationship between the two. This display shows the 3 distinct scenarios we resolved today, using specific symbols carved into birch bark cards to record the outcomes. The core operation remains the same every time. Check the 10s, and if they tie, check the 1s. But what happens in a final, unexpected challenge? Imagine 2 separate harvests that both have exactly 3 caches of 10 and 0 loose acorns scattered around them. In this final diagram, an equal sign sits centered between the identical values. When the 10s place and the 1s place tie perfectly, we deploy this final contingency to show that the 2 quantities represent absolute equality. 30 equals 30. Her work on the forest floor complete, Juniper tucks away her final acorn and dashes up the rough bark of the oak tree. By internalizing the hierarchy of 10s and 1s, you can rapidly and accurately compare any 2-digit quantities, skipping the tedious manual counting entirely.
8 10s beat 7. If 10s tie, ons decide.